Hi, in this video we will study the properties of the orthogonal projection of a vector onto a subspace and prove the orthogonal decomposition theorem. Well, throughout this video we are assuming that W is a subspace of Rn. Then for any vector V in Rn, we define two things: projection of vector V on the subspace W and perp V W. Well, perp is easy, just V minus projection of V over W, but projection of V over W, to be able to define that, we need to fix an orthogonal basis for W. So where U1, U2 up to UK is an orthogonal basis for W, then we define this to be projection of vector V on U1 add to projection of vector V on U2 and go up to projection of V onto UK. And yeah, that's the sum of the projection of V onto elements of an orthogonal basis. Well, the first property or first fact about this projection is that projection of V onto W is a vector. Yes, it belongs to subset W itself. How do you see that? Well, you know that projection of V onto W is sums of projection, but if you open it up, you see that projection of V on U1 is U1 dot V over U1 dot U1, then scalar multiplied to U1 and goes up to UK dot V over UK dot UK, and then scalar multiplied to UK. Well, these coefficients you see here, these are scalars, yes? So what we showed here is that this is projection of V onto W is linear combinations of U1 up to UK. Well, and well, any linear combinations of U1 to UK belongs to W, because U1 to UK is a basis for W. Okay, that's the first thing. The second thing is that, well, now that we know where the projection of V onto W belong to, how about perp of V over W? Well, this one belongs to orthogonal complement of W perp. And how do we show that? So it is enough to show that perp of V over W is orthogonal to U1, U2 up to UK, because the span of those guys is W. Okay, and if you know that, then just find U1 dot perp of V over W. Yes, this is U1 dot V minus projection of v over w. I'm opening it up, so it will be u1 dot v over u1 dot u1, then multiply to u1 minus u2 dot v u2 dot u2, and then scale and multiply to u2, and this will go up to uk dot v over uk dot uk, and then scale and multiply to uk. Now you can expand this dot product inside, and what you will get is u1 dot v minus u1 dot v over u1 dot u1, and then u1 dot u1. Yes, the others, the constant doesn't matter. We have, let's say, c2, then u1 is multiplied to this u2, so it will be u1 dot u2, and this will go up to ck u1 dot uk. The reason that those constants doesn't matter because these are orthogonal base, they form orthogonal bases, so dot product of any distinct element from that set is 0. And well, look at this guy, u1 dot u1 in numerator, u1 dot u1 in the denominator. This will be u1 dot v minus u1 dot v in the numerator, and the rest is 0. So then you subtract these two, you get number 0. So we showed that perp of v over w is orthogonal to u1. Also, you can show similar way to u2, u3, uk, and that proves everything. Well, now that we know one belongs to w, the other one belongs to w perp, an easy third fact is that if you add these two guys, projection of v over w and perp of v over w, these will add up to vector v. Why is that so? That's easy to see because the definition of perp is v minus projection of v over w, and this and that cancel each other, you get v. In other words, if I call this guy w, vector w this time, and I call this one vector w perp, what we showed here is that what we have shown is that there exists a vector w in subspace w and a vector w perp in w perp such that v is equal to w vector w plus w perp. Well, at least we showed there exists such a thing, and the orthogonal decomposition, basically we decomposed v into two pieces. One belongs to w, the subspace w, the other belongs to w perp. The orthogonal decomposition theorem says that this decomposition is unique. So with the assumptions above, there are unique vector w in w and vector w perp in w perp such that v is equal to W vector W plus W perp. Well, proof of uniqueness is not that difficult. You can check in the proof, but that is the decomposition. I have a vector and subspace. I can decompose this vector into two pieces. One piece belongs to that subspace. The other piece belongs to the orthogonal complement of that subspace. And the orthogonal decomposition theorem says that such things are unique. So it means that you start with any basis, do the projection, define the projection as we have, you will find W, vector W, and then perp of that will be W perp.